carry today also a little bit of India today. Yeah, thanks.
Thank you, Martin. Thank you. Hi, everyone. Thanks for coming for the presentation. And I will try to be slow today in my speech. I know that's a big problem. So I want to start with my experience or my education because, yeah, it's a bit all around the place. I did my master's in mathematics. Actually, the story is that after my master's, I didn't want to do a PhD. And it's weird that now I am in a position where I'm going to get a PhD. And yeah, I don't know how that happened. Then I was in, doing volunteering in Ladakh, India for a while. And I came across the project, ICE2 project, which you all know by now. So that's how I ended up in this by accident, actually. And then by another accident happened, which is I met Felix Keller from Samedan. And that's how I came into Switzerland. And then another accident happened, which is I met Martin through Felix. And that's how I ended up here. So that's the short gist of why I'm here. And why I did the PhD is now I'm going to get to tell you about. So the contents, how I structure the talk is I have an introduction section. And then I talk about a bit about the history or the tradition of how these artificial ice reservoirs came into being or ice stupas came into being. Then I talk about what we did in the university, how did we conduct our research through the science chapter. And then I talk about the results that we got in the technology chapter. And then I give an outlook of what is the future of this whole PhD. So I wanted to start with a bad news, which is half the world's glaciers are going to disappear by 2100. This is actually a conservative estimate. It's not exaggerating here. And in particular, there are around 2 lakh glaciers in the world. And most of the glaciers that will be disappearing will be small glaciers. Small glaciers are already close to villages and communities. And so these communities will be heavily impacted in the next few decades. And this is very important. Why? Because first of all, what does it mean when a glacier melts away? Actually, when a glacier is kind of healthy, it's big, it's large in area or thickness, when it starts melting rapidly, which is happening right now in many glaciers around the world, it gives a lot of water, right? That's what you would expect. But then there's a threshold called peak water, where either the area of the glacier gets very small or the thickness gets very small, and then it starts year by year reducing its runoff in the spring or across the year. And what is interesting in this graph, if you see, is the places where there is no snow melt or rain or groundwater will be heavily impacted by this trend. And that is what I will be getting into because there are many places like that, particularly in high mountain Asia. This is a graph from the IPCC report, which talks about climate change adaptation. And here you see that many adaptation strategies are actually practiced at large in high mountain Asia. And one of the reasons why is because there are many glaciers here and many people depend for their drinking water supply and irrigation on these glaciers. One of the practices that was highlighted in this report was artificial ice reservoirs, as I call it, or ice stupas, as it is commonly called. And there are basically 2 types of these structures. One is ice terraces, as shown here, and which is basically located at a higher altitude, and another is ice stupas, which is located at a lower altitude. So these ice stupas are kind of conical structures, and ice terraces are flat ice structures. In the rest of the talk, I will be focusing on the ice terrace type of structures, on the ice stupa type of structures or vertical conical structures, and not so much about ice terraces, but I will get back to ice terraces later. So about ice stupas. So how are these structures made? These ice structures, which are conical in shape. So first of all, you need to source the water to make these ice structures, and that is done via a pipeline. The water source is usually a glacial stream or a spring network. And because of the altitude difference from the water source, which is typically like at 60 meters higher than the outlet, which is where you build the ice structure very close to the household or to the farm, that altitude difference or gravitational pressure creates the energy required to run this whole system, right? And usually we also have the tradition of building some kind of a room inside the ice structure. And here you see one of these rooms made from trees. So then what happens is usually the ice structure builds up as the fountain water gets ejected from the fountain. And because during winter nights, the temperatures around -10 degrees Celsius, these droplets freeze naturally in the ambient air conditions, and then they accumulate below the fountain. Once the ice structure has accumulated below the fountain, you have to raise the fountain, or else the fountain gets buried in ice. And that's one of the maintenance efforts that is required while constructing these structures. Then once these structures are built, which is during the basically the freezing time is starting from early May, November, and then it ends in mid-March, which is, I'm talking about the northern hemisphere, particularly Ladakh, in the context of Ladakh. And then the melting time is after March to May, June, July, it could extend. And here you see one of these sites where we built for the first prototypes of these ice structures. And you see also the plantation plant below. So usually the structure melts for 2 months during April and May, and that's when the plantation needs the most water, which is what I'm going to show here. So what is happening here, if you see, once the glacier starts reducing its water supply year on year, and also if there is not much snowfall to adapt to that, then this is the typical scenario where these kind of artificial ice reservoirs are used, or ice stupas are used. And where they provide water is during the months of April, May, or June even. And this is when the irrigation cycle starts in these particular areas. And this is when the water demand is very high, but the glacier is not supplying enough water, or there's not much snow melt to provide more water for the farms. And that is why these artificial ice reservoirs are used. So if you don't have these structures, what happens typically is you basically lose this whole irrigation cycle. And that means basically half the income of the farmer. So this is why it is widely practiced right now in many regions across many mountain regions, particularly in high mountain Asia. And also one of the reasons why it is being practiced even organically by many farmers here is because you don't really need so much money or financial investment to do these structures. Or for any water storage technology, you just need a pipeline. First of all, you need a pipeline, right? And then you have the infrastructure to build the water storage device itself. In the case of the ice stupa, the pipeline is enough. If you have weather conditions, you can build it. So that's why there's no barrier as such to build the ice structure. But there are other barriers, which I will talk about later. So now we're getting into the history of where does this idea come in of the storing water as ice structures, or here in the history it's called artificial glaciers. And here, for example, you see one of these artificial glaciers in Gilgit, Pakistan, which is like just above in the border of India and Pakistan. And the history of this whole artificial glacier concept actually originates in traditional practices. Very typical traditional practices where basically the people here in these regions believed there were genders associated with glaciers. How they believed it is basically they thought female glaciers give more water and male glaciers give less water. You can also imagine this in terms of what the peak water, which I mentioned before, where glaciers start giving lesser and lesser water after a certain time. And this is what I believe they kind of were talking about when they were talking about male and female glaciers. And how they practice is also very interesting. Here you see basically they had to break ice from a male glacier, which they identified, and a female glacier they identified. And then they used to carry this ice in these baskets, as you see, and in a very, very particular way. Basically, you cannot keep the basket, you cannot unload the basket at any point during your journey. And this journey usually takes like a few days, where you travel from the male glacier to the female glacier, and you find the right place to plant this ice. And even during this journey, you are not even supposed to talk with each other. So it's like a silent journey with a heavy load on your back, and for across many days. So that's how serious they were about doing this, right? And what they did when they actually located a particular kind of a cave or a location where they believed a new glacier could develop. And there they stored this male glacier and female glacier together with some water in caverns and hay to protect it. And they believed that if they let this be there, then a new glacier will develop. And they were very serious again about this, and they never allowed anyone to enter these kind of holy sites. And they also had a ceremony to inaugurate this site with sacrifices of animals and so on. But another point to note here is that they actually thought a lot about where to put these, where these sites should be located. They usually focused on north-facing slopes, which are typically shaded from sunlight, and there are some records where people are saying that the glacier grew here because we started putting here, but that's still debatable. So there are many, more than science, there are some scientific takeaways as I showed you, but there's also a societal takeaway where people used to care or be very concerned about the retreating glaciers, right? And this is also something going to come big later, because this kind of practice actually inspired this whole ice stupa. And the name itself is a name which local people called when they saw the ice structure first built, right? So because it looks like a typical stupa, which is a Buddhist symbol, and Buddhism is kind of popular in this region of Ladakh. And for me, when I was involved in this project, there's also a new meaning here, because in Buddhism, there's a practice called mandalas, where they build these structures of sand, basically colored sand. And what they do is very interesting here, because they build these very intricate structures, like a team of monks, 4 or 5 people for a week. And then at the end, they just wash down the structure, wash down the painting, and forget about it. And in that way, I also feel, because when I was building these ice structures together with the people in Ladakh, it was like the structure was built with a lot of effort across the winter, and then you watch it melt and disappear. And in that way, it also has this kind of a religious symbology here. And it melts and melts, and then there is a plantation which is being greened there, and so you see this transition of ice becoming water and then becoming into these plants, right? So there are many ways. So across the last few winters, specifically like 6 winters, ice stupas have come in a big way in this particular region of Ladakh, northern India, and they are being celebrated in many different forms. One of the forms which I indicated is through this Buddhist symbology. And in fact, in one of these ice structures, typically, as I said, these ice structures have tunnels inside them. And in one of these tunnels, we actually had a, again, symbolic ice stupa, so made a sculpture of a stupa. And then it became a temple, literally. So there were people, hundreds of people coming every day to visit and pray inside these tunnels. And that was also very powerful to witness. Of course, then there are also many other activities, basically like ice climbing events that are happening on these ice structures. Sometimes there are people also building cafes inside these ice structures, and so on. So it's kind of interesting to see how society has accepted this kind of a new water storage technology in that way. Now I'll go into the science, or why I started this PhD, right? So as I told you, I have been building these structures for the last 6 years. As I began as a volunteer, and then I worked across the winter to build these structures. And whenever I build these structures, I always wonder, because you have put so much effort to freeze the water, but are you really freezing water, right? There's so much water coming out of the fountain. How much of that water is freezing? And how much of that water is just flowing away, right, into pools? Or in the summer days, how much of the water is evaporating into the atmosphere? And we also witnessed a lot of differences in volume across different villages where we build these structures. Here you see a collage of all these structures that we have built across the last few winters, and you see the differences in shape, you see the differences in volume, and it was very confusing why this was happening. Of course, we had some clues in the way that maybe this shadow area, so the ice structure builds, but still the differences were very significant. We had differences of ice volume, maximum ice volume, from 1 million liters to 20 million liters across a very short area of land, like across this, let's say, in the scale of a canton, you can see that such a big difference, right? So the motivation of the whole PhD was to understand what were the meteorological influences or weather patterns that were favoring ice formation. And second, also was to understand what were the water losses involved in during the construction. And yeah, and that's what I will focus on right now. So to understand this, we just took, we had several measurement campaigns. I will focus on only one winter, which is 2020-2021, where we made ice structures simultaneously the same winter in India and Switzerland. Here you see the pictures of both the ice structures. And what is interesting to note is we tried to zoom in into all the processes that were favoring the ice formation. For example, here in India, the structure is much, much bigger than the Swiss, right? So why was that happening? We wanted to understand that. So for that, we first had also a time-lapse camera placed in the Swiss side. Here, Guttannen, Daniel is here. He was managing the Swiss side. So, so here you see the time lapse of the whole ice structure evolving in Guttannen, right? What is interesting to note is we didn't have any tunnel here. We just had the fountain. And the interesting to note is how the ice structure evolved, across the winter. So you see there is a perimeter of ice forming because of the fountain. There's a distinction between the color of the ice that is being formed by the fountain and the snow. And this is also very important, and how the ice is forming. So what we observed is that the perimeter of ice forming around the fountain was actually constant until the fountain was on. And then when the fountain was switched off because it was too warm or to make ice, then the ice structure slowly melted away. And you will see some of these rapid melt events. For example, here, what happened here is there was a rainfall event actually. And that drastically melted in the period of 24-48 hours. And in the summer, it just keeps melting away. And we had to figure out a way to understand, to model these processes that were both freezing the ice structure and melting the ice structure. Melting the ice structure, there is already a lot of literature, which applies on glacial surfaces. And this is still an ice surface or a snow surface, so we could apply. But freezing the ice structure, we had to find new ways to really model these. So I will first show you. Yeah, I'll first show you all the measurements that we took to first prepare ourselves for this modeling effort. We had weather stations placed both in the Indian side and the Swiss side. And here you see the rough mean measurements of that weather station. First of all, the altitude was completely different. Indian side was around 4 times higher than the Swiss. The temperature in the Indian side was colder, around 2 degrees Celsius. The Indian side was also much drier than the Swiss. And the radiation, the solar radiation, also around 2 times higher in the Indian side, and the wind speed was also higher. So, and then we also conducted a lot of measurements of how much water is going into these structures, right? So how much water is the fountain spraying? For that, we employed flow meters in both the sides. And you see here the mean discharge rate measured by the flow meters. In the Indian side, it was around 60 liters per minute for 830 hours or 800 hours. And in the Swiss side, it was much lower, around 8 liters per minute for around 2,000 hours. We also had to understand this process of how the fountain shaped the ice structure. For that, we invented something called a spray radius. Here you see, for example, in this picture, the perimeter that the fountain formed versus the natural snow, right? So this perimeter or the radius of this perimeter is how we define the spray radius. So in the case of the Swiss side, it was around 7 meters, whereas in the case of the Indian side, it was around 10 meters. So in this way, and then the most interesting thing that we did is we also conducted drone measurements to actually evaluate what their volume evolution is, like every week almost. In the Swiss side, in the Indian side, it was, yeah, it's difficult to conduct every week. So we had to manage with what we collected. And here you see all the measurements plotted. In the top half of the figure, what you see is the Swiss side or Guttannen, where each of these purple lines are measurements. Also to note, the first point here, 13 meter cube, this is also a measurement. This is the volume of the twigs that were used in this particular year. And then in the Indian side, also purple lines are drone measurements. One person physically went there and performed a drone survey. And in the first point here is again another drone survey, which calculates the ice already present in the site. And this is the result of the model. So as I said, the attempt of the model was to, model never saw the purple lines. Huh? The only thing that the model input was the weather measurements that we made hourly, and then the fountain measurements, or how much water is going in through the flow meter. And the only thing that the fountain knew from the drone was the first drone survey. So we fed the model the first drone survey, and then it predicted the rest of the things. So you see that we can believe the model. Why? Because the model can, in a way, say what the drone is going to say. And what I would like to focus on is also the output of the model, in the way, what is the freezing rate, right? So we observed that the model was saying around 14 times difference, right? So in the Swiss side, the freezing rate that the model predicted was around 1 liter per minute, and in the Indian side, it was around 14 liters per minute. Now I want to go into our questions that we started off with. That is, what is the water losses that are happening? What are the surface processes that are actually creating this bigger difference, of freezing rate in the Indian side versus the Swiss side? And for that, we have to go into processes that are happening on the surface of the ice structure. To go there, first we have to understand how the model functions. So the model algorithm that we used is basically, you have, as I said, the input data, which is the weather fountain data and some drone measurements. Then you have the surface processes that are happening on the surface. This could be conduction, convection, sublimation, evaporation, long wave radiation, short wave radiation. Then there is also another process happening, which is how the shape is evolving, how the radius of the cone that the model imagines is changing, and how the height of the cone that the model imagines is changing. And through this, we get the surface area of the structure, and the surface area multiplied with all the surface processes, we get the volume, right? So this is in a way a simple simplification of how the model functions. And now, as we have measured all the mass input to the fountain, we know that in the case of the big difference between both the locations is that the Swiss side had a lot of snowfall, and this will come in later. So there was some snowfall in the Swiss side, but in the Indian side, most of the water input was coming from the fountain itself, right? And then the way the model changes the shape is during the time when the fountain is on, as you observed in the video, the radius of the cone cannot go beyond the spray radius of the fountain, which was again measured on the side. And then during the time when the fountain is off, then the slope of the cone that the model imagines is kept constant. And this is how it varies the shape across the whole period of observation, which is in this case around from December 2020 onwards to April 2021 onwards. So, and then we have the surface processes. I will focus on only the surface processes which the model found significant. And in this case, it was the sublimation process. Or, sublimation is an interesting process because what you have in the case of sublimation is you have a mass loss happening, of course. Some of the water, some of the ice that is on the surface, it is vaporizing and becoming into gas and then escaping away. But you also have a freezing energy gain happening. How? Because sublimating a ton of ice is equivalent in energy to freezing 9 tons of water. That means if 1 ton of ice sublimates in this hour, then the next hour, there's 9 tons of water that can freeze on the surface because of the cooling down of the temperature of the surface, right? And this is the process which actually caused a big difference in terms of the freezing rate of the Indian ice stupa compared to the Swiss. Then the next process which I want to focus on is solar radiation. So as I said in the beginning, shortwave radiation which was measured in the Indian side was around twice that of the Swiss side. But the impact of the solar radiation on the ice surface itself is drastically different. In the case of India, the impact was half that of the Swiss, even though the solar radiation was much stronger there. Why is this happening? Is because of the way direct solar radiation impacts the ice structure. So if you see the ice structure from the top, then the direct solar radiation impacts only a half circle of the surface area. And then if you see in the horizontal angle, it impacts only a triangle of this surface area. So in total, only 30% of the direct solar radiation impacts the ice structure itself. And what this means in practice is, In the case of the Indian side, there was all the solar radiation was mostly direct solar radiation. So most of that could not be absorbed by the ice structure. Whereas in the Swiss case, there was some diffuse solar radiation, which doesn't have this directional behavior. All of the surface area absorbs diffuse solar radiation. And that's why you see a big difference. So this means that the Swiss side melted faster because of clouds, more clouds in the side. And then, yeah, so I explained this, yeah. And then the last thing which I wanted to take away from the model is the fountain, right? How did the fountain impact the whole evolution of the ice structure? And for this, we first sum up all the differences in the processes across both the ice structures. So what you see here is the difference in terms of freezing process. So for the Indian side, the freezing processes were 4.5 times stronger than the Swiss side. But all these processes are happening on the surface of the ice structure. So the surface area is very, very important. And that surface area is determined by the spray radius. And because the spray radius of the Indian fountain, in this case, was around 10 meters higher, 3 meters higher than the Swiss fountain, you have a 3 times higher surface area for the Indian ice structure. And so you multiply the difference in freezing process with the difference in surface area, and then you get this value of 14 times higher freezing rate of the Indian case. So what is also interesting to note is the water losses involved in both the cases. Even though the locations were drastically different, the water losses that we observe are very similar. What you see here is all the water losses loss components. There's fountain wastewater, which is basically all the water that is coming out of the fountain, which is not interacting with the ice surface, which is just flowing away. Then you have vapor, which I showed you, sublimation process. And then there is ice formation, and then there's meltwater, basically ice that is melting. So what you see here, the orange highlighted parts are water losses, right? So around 80% in both the different locations, there was water loss. So only 20% of the water that is being fed to the fountain was being used to make the ice structure. Now, I want to go further in using these results of the model, right? So what we did in the next step is we zoned in these two big problems of forming ice stupas, which is, the first is, as you observed, the water loss is very, very high. And the second is also interesting. It is that in the Indian case, there was a lot of maintenance happening. Why? Because as you see here, these stepwise functions of this red line that you see in the graph, this is the discharge rate of the Indian fountain. And what is happening is the discharge rate is going from 60 liters per minute to 0 liters per minute, and several times across the whole season, which is from January to March. And eventually what happens is, people just give up. What is happening here is, every time there is a drop in discharge rate from 60 to 0 liters per minute, there is a pipeline freezing event happening on the site. So what that means on the field is, each person has to come to the site, check if the fountain is functioning. If it is not functioning, they remove the fountain, take out all the ice from it, and that's how they repair the fountain. And you see here, for example, what is one of these pipeline freezing events that have happened here. And so this is a very tedious process. And usually what happens, we have observed in Ladakh, most of the ice stupas, they do not utilize the whole winter, because during the peak of the winter, when actually ice should form much better, there's also always this problem of pipeline freezing events happening. And so people give up. And that's why even in the previous ice structure, if you see that by early March, they had to give up and just stop, even though the weather conditions were very good, right? So yeah, so these are the two big issues that we wanted to fix. One is high water losses, and another is pipeline freezing events. So how did we design the strategy to do that? So that's what is going to be the next part of the talk, where in Guttannen, last winter, actually, not this last winter, we had designed construction of two ice stupas. These ice stupas were different from each other in the way the fountain was fed water. We call one fountain an non-scheduled fountain, another a scheduled fountain. Why? Because you also see the fountain shapes are different. Because the way the water was fed was drastically different. In the case of scheduled fountain, we wanted to use the model's output. So we ran the models real time, and based on the model's output, which ranged from 2 liters per minute to 15 liters per minute, we wanted to run this fountain. Whereas in the non-scheduled case, We just wanted to use all the water that we have. So that's why, and this is a typical scenario in Ladakh where they just spray all the water that they have. And that's why we called one ice stupa a manual ice stupa and another as an automated ice stupa, right? And how we operated the automated system is by through these devices. So we had a weather station, we had a logger box or a control box, which had a Python program running, which is the model running in it. And then we had a user interface through which we can manually control or even give commands to the program, right? What is happening here is you have in the pipeline, you have a flow meter, which tells you exactly how much water is flowing through the pipeline. Then you also have a ball valve, which is controlled by this control box. So this ball valve can close to 0% and or open to 100%. And based on that, the flow changes from 0 liters per minute to 15 liters per minute. And this flow, again, as I said, is decided by the model. So the model tells the control box how much you should spray in the next hour, and the control box opens the ball valve, maybe let's say to 30% to allow only 5 liters per minute based on the model. And then the fountain runs based on that. So this is what you will see in this figure. First, I wanted to focus on the non-scheduled fountain, right? So the blue line that you see on the bottom half of the figure is the non-scheduled fountain discharge rate. And the red line that you see is the scheduled fountain discharge rate. What is interesting to note is the temperature variations happening. So as I told you, the model is functioning real time. So it uses this temperature data to tell how much water should be sprayed. Okay, that is coming in the red line. And first, as I said, in the non-scheduled case, it is not being, it's just being, all the water is just being let through. And so what you see here is first the maximum amount of water available was around 14 liters per minute. And then what happened in this step, this event was the fountain height was raised, I think from 4 meters to 5 meters. And then because of the raise in fountain height, the discharge rate lowered. And then what happened here is that the temperature got very low, so low that the unscheduled fountain or the pipeline that was supplying water to the unscheduled fountain froze. And this is why there's no more water sprayed into the manual ice stupa. Now going into the automated ice stupa or the scheduled fountain, what we see here is how the model behaved based on the temperature. So all these cold events, which is like temperatures of around minus 10 degrees Celsius, the model tried to spray as much water as possible. And that's what you see in these peaks here. As I said, the peaks are lowering because of the change in the height of the fountain. So through this, and again, what another thing to note is the fountain never froze, even after the unscheduled fountain froze, right? So it was able to function even as late as April like in the middle of the peak summer, it found time to spray the water. So, but what another interesting thing to note is the amount of water, even though it was completely different, amount of water used in both the fountains, the ice volume that we observed through the fountain, through the drone surveys and through the model were actually very similar. Again, as I told you, the drone surveys here are marked based on dots, and the model predictions are the red and blue lines. And you see that the ice volume was not so different in both the cases, even though the water supply was very, very different. So in this way, we found a way to make the water input to each of the ice structures very, very different. In this case, we had a water use efficiency gain of around 8 times higher. In practice, what it means that we can use the same water supply to build 8 of these structures rather than one structure, right? And this is how what we found through this effort. Next, I want to go into, okay, now that we have found is what is next, right? So what does it mean in the case of climate change adaptation? What does it mean in the case of people struggling to find water to irrigate, in the context of rapidly melting glaciers? So the question really is, can these structures actually give enough water supply per day which is comparable to whole glaciers, right? And the answer is no, in simple terms. But what is happening in Ladakh is interesting in the way that there are some villages which have been deserted because there's no more water supply going into these villages. But there have been events where using these ice reservoirs, they were able to cultivate a lot of potatoes and plants in these villages. But still, it's not in the scale of a whole village. It's in the scale of one farmer, right? So these structures typically give around 11,000 liters per day, which only supplies water in the scale of a meter square irrigation land, So whereas in this village scale, you need a kilometer square irrigation land you have to provide water to. And that is where these structures are lacking right now. So for this, what we want to do at least is there have been some structures which have grown, which have either been, which have never melted across the summer. What you see here is on the left is one of these structures in Shara village, where it lasted across the summer and never melted until even the next winter. So it could be continued, to freeze. It can be continued in the next winter to freeze. Whereas in the right case, what you see is these structure is ice terraces, which are these flat way of building these ice reservoirs. They have been built in areas comparable to natural glaciers. So if they melt, they will actually give water like 1/5 of the water supply of the natural glaciers. But they are much more difficult to build and require even more investment in terms of, you have to build these embankments of stone across these valleys so that the water freezes behind these embankments. And that's a huge, very labor consuming effort. And we want to, so we want to combine the advantages of both these kind of construction methodologies. So in the case of ice stupa, you don't really need so much effort if you solve this pipeline freezing issue. Whereas in the ice stupa, the ice terraces, the advantage is you can build structures at scale, like comparable to natural glaciers, if you have the water supply, of course. So we want to combine the advantages of these two strategies to build ice reservoirs in the scale of artificial glaciers. And with that, I would like to end this talk. I would like to, I am very grateful to all the support that I've got through, in terms of field work. I got support from Swiss Polar Institute to do my field work in India. And also Daniel is here from Guttannen. I got a lot of support from them, and there have been many people I cannot, I can keep telling their names, but yeah, there's still so many people. And also, I would like to introduce the next part of this project, which is we have built a company around this whole idea. It's not just about ice reservoirs here, it's also about water management in general, because as I highlighted, water resources in these kind of regions are very limited now, and the next few decades, they are going to be very, very stressed. And this is why we thought it's important to work on water management as a through different strategies across many mountain regions. And of course, we want to start off with the artificial ice reservoir approach, but we also will be broadening our interventions soon. And I would like to end with a slide video I have of life as a PhD student. And it's a short one. And I would welcome any questions that you have.
Thank you very much actually for this very, very nice presentation. I think most of us has really taken a lot with that. And of course,